Okay, so today we will talk about now that we basically cover what we want to cover for system skill, right? Aside from the obvious that the next class in your prerequisite chain, I guess the chain of class requirements is the computer system and architecture class, or sometimes we call this PCSA class. I want to kind of talk about what are the different area in this whole big world of computer science that uh, that things you learn from this class would be relevant, right? Because but I think by this point, many of you might be questioning like, hey, I program in Python, it looks fine. Why do I have to learn C? Why do I have to learn assembly? Why do I have to learn computer organization? Um, in fact, that's quite multiple area, right, in computer science that would benefit from knowing this fundamental basics. So to do that, we'll first do a quick recap about what we just covered, right? So in the beginning of this class, we went through Linux, and this is give you a sample of Unix-based operating system. If you have to work on a anything from DevOps to just coding, through working in Linux, through system programming, through hacking, through building, even building the hardware. Knowing Linux is crucial to your career because it basically is one of the OS that's really common. So it's good to know the basic commands, right? And then we transition to C. It's a language that's kind of really close to the hardware. And then we get closer to the hardware with assembly. And we kind of follow that up with like, okay, now that we know these languages, how does the data and the program get stored, represented, and how does the basic components of the computer work? So this becomes like an intro to the, sometimes we call this computer organization, sometimes we call this like intro to computer system. Uh, what we have here is basically we are teaching you the basic of how the computer works, and anything. So now this quick disclaimer: everything that come after this is my own opinion on computer system, computer architecture, distributed system, network as I understand. Right, so these are my opinion disclaimer, but I mean another asterisk is I'm one of the expert in these area. So what I tell you, while there can be some disagreements with several people, these are my opinion. Um, what I'm trying to tell you is likely to be relevant in choosing whether you want to kind of pursue any of these area or not. Right. So what's next? Now that you know system skill, we are teaching you some basic building block so that you have the ability to follow it up and work on topics uh, that basically involve more of the control of your computer, and how I should put it, right? This can range from computer system, distributed system, cloud, IoT. Anyone here heard about the word IoT? So what's your impression of the IoT? Let's say I said this word IoT out loud. What would be showing up in your brain? Like, what's your impression of this Internet of Things? What does it mean? Yeah, it's gonna be like interconnected devices that come from different companies that would connect and use the internet, and that's actually not as correct as the whole area of IoT would govern, right? And see you, that's awesome. So it's a connection of actually multiple devices, and the device can produce its own events, right? So as an let's break down this name a little bit because I feel like the name is perfect. But because people who doesn't really understand how the computer work, especially many programmers and many developers and many companies, quote unquote IT company in Thailand that doesn't have a lot of system knowledge, look at the term, and what they understand is like, oh, okay, I connect things to the internet. Is that IoT? Seriously, like if I connect something to the internet, can I call that IoT? Sorry, I was laughing about that. It's like, then wouldn't my computer is an IoT device, right? So what's unique about IoT? So the term, it actually, if you break down this term, it's Internet of Things. What are the things? Things are devices, computer, server. Basically, things can cover any compute elements, right? You basically provide the interconnection substrate to connect all the devices that can range from sensor, your computer, embedded processor like Raspberry Pi or NVIDIA Jetson. These are small computers that you can kind of throw around and use it to measure different things in the room. It can be the Amazon Echo, right, that has Alexa on it. You can, sorry, I just want to make sure I don't trigger those things. I have that like around here in the house. Um, Also the Google Nest, Google Home, that is an app that connect all the devices together, right? So it's a network, right? It's a network of things. It doesn't have to be connected to the internet. That's like where many companies in Thailand got it wrong. It's like I don't have to connect to the internet. I mean, to make it work, right? I can have a security system that would work as a standalone system too, right? But I would utilize multiple devices that get connected. I should be able to scale, right? So if you say you want a smart city, are you gonna be able to scale to having thousands and thousands and tens of thousands or hundreds of thousands devices in a city and they can talk to each other? Those are not easy tasks. And I don't see a clear solution yet because most of the solution right now is not scalable. So we'll see where this area lead us. There's quite a lot of new emerging topics that can be interesting. So this is basically the reason why I brought this particular keyword up, including cloud, right? I'll talk about cloud in a bit as well, because many people in Thailand, especially, misunderstood what is cloud, right? And this is my reflection on this because I work closely with computer systems. I'm the only few people in the country who actually have actual experience, right? With building or at least like read papers and try to gain knowledge on how to build these kind of systems. It's like when people take this terminology wrong, right? I want to make sure I try to correct it so that they understand it better. Uh, so in the IoT, basically it's like a bunch of devices that are connected in a network. You want to make sure they are reliable. You want to make sure they can scale. You want to make sure they can integrate multiple types of devices. Those are not easy, right? Cloud. Anyone heard about AWS, the Amazon Web Services? Or cloud computing? Anyone heard about the word cloud computing? Right? So cloud computing, there are kind of two flavor of that. There's a user side. I built a program, I can launch it to the cloud. That's nothing. That's like software programming, right? But then there's a people, engineer and scientists that work on how to build the cloud, how to maintain the cloud. We don't have that many people who know how to do that in Thailand. So this is really, really a rare area. And I will talk a little bit more about like job opportunity as well, about what if you go into the computer system, because that's where another group of misunderstanding that also stem from many professors in Thailand as well. Uh, so what's next? What else, right? Computer network, right? How to build a protocol, how to make sure the computer can talk to each other. Computer doesn't have a leg like you guys or us, like or me, right? Where I can go and walk to your friend and talk, right? The computer is a stationary thing, and somehow you need to build the network so they can talk and communicate between different computers. Computer security, right? There's the cryptography area that's involve more maths and more algorithm. And then there's a system side of security, which kind of govern like I know the computer, how it works. And then I'm gonna check like, are there any holes in there that I can hack into so that I can patch it and so that your data is safe, right? There's also compiler and compiler optimization, the magic behind translating your code in certain language like C, Java, Python into something the machine understands, right? Database system, how to keep a record of data and how to look it up quickly, how to update your data quickly, how to maintain different structure, how to maintain a non-structured type of database, right? Uh, Storage system, which kind of govern how do we interact with, say, things like storage, SSD, hard drive, right? How do you build a file system, right? So if you use Windows, you might have heard about the word NTFS. NTFS is the way Windows keep track of the file and how do they actually allow you to browse the content in your computer, right? That's ext4 that's used by Linux. The old version of Windows is FAT32. Each of these formatting, right? They have a different flavor that has pros and cons that come to it. Parallel programming that kind of involve the ability to write program in parallel. So if you know C, if you know how the computer works, you start to notice how you write a better parallel program. Embedded system, right? These are system that are similar to, for example, this thing has microcontroller that can control my air conditioner, right? I can use it to turn temperature up and down. It's something simple but cheap and really, really power efficient. Powered by two AA battery, and that's all I need, right? It's simple, it's cheap, I can use it everywhere. It would interact with a lot of input and output from the user and directly do whatever task is programmed to do. And then there's a field that's close to home for me, which is where I would identify as I'm a computer architect, right? Computer architecture is like, okay, how do I build a computer? So we'll go through this some of these things from the list, right? So let's start with computer system, right? So if you are interested in building a computer system, definitely the computer system and architecture PCSA class that's available next semester. It will talk about three different flavors of topics that you should know as a programmer. We'll begin with Ajahn Sansan, who will be teaching you guys the OS, right? And then it will follow with Ajahn Kanat, who will be giving you knowledge about computer network. And then I'll be teaching, wrapping up the end and cover the computer architecture. These are kind of like the key three elements of computer system and architecture that basically cover. If you have you heard about the front end and back end? The word front end developers, back end developers. These are like a backdoor on the back end kind of thing, right? This is like the thing below the iceberg. This is like back end. It covered how does the computer work. How do you write a program to control your computer? How to write a framework to interface with the back end? How to make sure all the framework would be behaving and don't kill your computer, right? So the computer system track, right? The computer system track uh, is about how to build a functioning operating system. Things like kernel hacking, how to manage all the running processes and tasks, right? Things like task scheduling and load balancing. And I'd love to compare this to, like, let's say you have a big group project, right? Let's say it's a project of 5 people. Do you prefer that you Oh, yeah, you can take the computer system and architecture class. That would cover the three area OS network and architecture. And then if there's a demand, there's another separate, like full-blown standalone special topic on each one of these. A special topic on OS, special topic on network, and special topic on architecture. These are demand driven, so if as long as there are more than 7 people that want to take the class, inform us, we can open that in the following semester, essentially, right? the whole reason why we have this PCSA class is not everyone want to work in the OS. Not everyone want to work in architecture. So they'll be kind of like, hey, let's combine this and make one class that. Hmm? Yeah, I think that's the class that said the special topic on computer science where it's a flexibility that we can add like whatever topic that year of students or that group of students would like to learn. So we can open that for architecture, database system. I think that's already a database system. That's not a special topic. uh, but things like file system, network, OS, right? These are rare, to be honest. I would say most programmer in the world, I would categorize like maybe 50% would work on software, or more, right? And then only maybe 10 to 20% would work on the OS or the network, right? So these are more rare, and that's why we make it special topic. Uh, but yeah, so let me compare their task scheduling and load balancing to let's say you run a group project. Would you be happy if you are the only one in the group who have to work and no one else work? Versus another case where I have someone who managed the distribution of work so that everyone equally work equally and the task assigned to each people completely match with the skill set of each person in the group. Which one is better? I mean, obviously the latter is going to be better, right? That's the OS. The OS have to run multiple programs. The OS becomes this manager say, hey, this part of the program go to the CPU. This part of the program, oh, you want to render graphic, go run that on a GPU. Why are you here? Go run it on a GPU, right? The OS will perform task scheduling, it will perform load balancing. How do you manage data mapping? How do you make sure that the data are mapped to different part of memory, different storage devices? That actually new technology comes out that actually, to be honest, in my opinion, is really exciting. That can you can use different types of memory, different types of storage, right? How to handle page fault? How to handle page fault between the CPU and the GPU? This is actually a really active research topic right now, right? How do you manage all the shared library? Um, yes, obviously, right? Because CPU, as the name suggests, right? It's general purpose. You can run whatever you want to run, right? You can write a program that render graphics on the CPU. But because of the nature of the algorithm, it maps really well with the GPU. That's why the GPU is really fast at rendering graphic and really slow at running certain things, right? The CPU and the GPU has a really contrasting trade-off. Some program will be fast on the CPU, some of the program will be really fast on the GPU. So if you know, for example, DOS are trying to make that guess and perform different scheduling, right? The system can do that. Well, I mean, hopefully the system can do that. This is our still research area, right? We are still trying to figure out what's the best thing we can do. So what else, right? How to build a functioning cloud infrastructure, right? Imagine, let's say you're Jeff Bezos, right? You're rich and you have a bunch of server at Amazon. What I can do is I can rent out the time for people to use my server. That's cloud computing. How do I manage the server? How do I manage all the client, right? You can probably imagine a scenario for like just use system skill server for your for this particular example, right? Let's say you go there to system skill and you by accident you run a program that cause memory leaks that use all DRAM. And then your friend in the well, let's say you're in 15 or it's 1502, right? The lab. Your lab at MUIC, is it 1502? Oh yeah. Sorry about that. I hope you guys can go there soon. It's actually a pretty awesome. It's a big room that is a nice working space. Um I heard my TA were thinking about like have a shabu in there. I'm not sure that's a good idea, to be honest. So yeah, this is where the students hang out. Uh Don't do crazy things. And try to keep it clean too. But anyway, so where do I get here? Actually, I forgot how do I get here? Oh, so okay. So your friend who are working on that program in the lab want to log into system skill, but you use all the memory. So what would happen to your friend? What would happen to your friend? Like you turn around like, hey, can you log into system skill? I somehow cannot log in. I can, I guess, but it's really slow. What happened? And then you turn to your friends like, wait, you're running something on there, right? So one user can deny someone else the machine because of some accident, some bugs. I can potentially write a program that would crash system skill, right, by accident. So when you are a cloud provider like Amazon or Microsoft or Google, right, you want to make sure you build this cloud infrastructure so this never happen. There are signs behind how do you ensure good load distribution? How do you ensure isolation where one user cannot impact another user, right? This also can also include things like distributed computing and IoT. These are kind of like the topic under the same umbrella, right? People here in Thailand talk about cloud computing like it's a software topic. IoT is like a software topic. No, it's a computer. It's like a full-blown computer system and distributed system topic. The hard problems are there. It's not about how to build the software. Those are easy. Um, it's also governs like how to build a high performance computing cluster, right? These high performance computing cluster are really high end machine that are used to run many scientific computing, many of the experiment. For example, right? You can run the program to figure out the genealogy tree of the COVID virus. For example, they look at how it mutates, right? How do we get here, right? I guess having bad vaccine can get. Sorry, I would like to joke about like Sinovac, but anyway, so you can use this machine to analyze the RNA of each generation of the COVID virus, right? And then you can try to figure out what happened, how does it mutate, so that we can build the next generation of vaccine that we can hopefully protect against the new I would call it John Ray now because there's so many of them. It's so easy to mutate, so we need to keep track of that using this high-end computer. There's actually a project in Thai SC, I would say I'll call this one of the computing center, a supercomputer center in Thailand. Actually, fun fact, next year, I think next year they are going to have one of the fastest, if not the fastest, supercomputer in Southeast Asia, and that also includes Singapore. That researcher in Thailand can use, right? These awesome projects. They also have another project running there right now that try to measure PM2.5. How many people here are all suffer from this thing, the PM2.5 problem, the air pollution that has been like big problem in Thailand. And for those of you who are in China, I'm sure you have that too. So actually they are trying to simulate the model so they can predict where the bad air is going, right? Uh guys, don't get used to it. This is bad. We should like me, right, as someone who's in a job market in the middle of my career, I should make things better. So it's my job to kind of try to tackle problems in the world, right? So my mindset is like, okay, these are bad. How do I contribute to make things better? Rather than how do I take profit? This is a wrong way to think, right? Think about how do you contribute to humanity. It's like there's a much better, a much more noble goal, right? Anyway, so when I was in the US, right? when I was in the US, I never even know about this like poor air quality when I'm walking around. You can walk around, there's no problem. PM 2.5 never go above like 20, right? And now in Thailand, like oh, the air is so bad, right? Um, Oh, yeah, that's awesome. You can have the yes, that's actually quite a bunch of IoT tracker that can be set up around at different location, and they can be linked in the network so they can send information for everyone to use and know like, oh, okay, the air quality is bad today. Let's wear the N95 mask, right? Rather than a normal mask to guard us against COVID. Um, so yeah, so these are what we can use the high performance computing for. You can also use it to run the simulation for tracking global warming, tracking how the carbon dioxide that we produce, right, as a humanity in general, like lead to the acceleration of global warming. Um, we can another different topics besides this high performance computing, how to build, how to maintain, are like how do I ensure that I use a system and I see the same set of data eventually? Let's say your friend updates on something on their profile in the Instagram or uh, send you a text, right? How do you know? How do you make sure that the text, for example, arrive at your computer in the same order that gets sent out, right? Because otherwise it's gonna be so confusing, right? If I send you the text, say, hey, what's up? Let's go get dinner. But you receive it as let's go get dinner. Hey, what's up? It's gonna be what? Are you drunk? Right? So this is basically something that also kind of involve how to time things and make sure the thing arrive in the order that everyone see, right? Uh, Generally, this is what many people would call back end, right? But the term back end is too vague. This is like again, as I said, this is like kind of like a backdoor to the back end, which is like housing all the system, all the back end that you developed, or the back end that you deploy, right? So that's computer system. The other kind of really interesting topic that many people didn't realize is compiler, right? You write a code in a program. How does it get translated into assembly? How to optimize your code into an even faster assembly? How to represent a program that's way easier to optimize the code, right? What's the best method to map your program to hardware? Apple came up with their own chip. M1 processor use ARM architecture. How do I change my compiler so any program written for Intel and AMD chip will run on this M1 processor, right? It's a huge task for the compiler people to figure out. Um, how are you going to deal with loops? Can you make the loop faster? How to deal with data access? How to make it more cache friendly? There's also another side topic on programming language. So we already changed the name of the class. It used to be called OPL, and now it's called Parallel and Functional Programming. Functional and parallel programming. Ajahn Kanat is teaching this next semester. Typically, I teach this. Next semester, I'm on a kind of like a maternity leave. Um, so I was just handling the PCSA class toward the end when I have to cover the computer architecture, and then I'm likely to come back and teach the parallel and functional programming in the future semester. This class will talk about the trade-off of different elements in your language in the way you program. What's the data type? How does it work? How do I reflect the data type so that future lines in your code know what exactly is going on, what's the function call, and how to write the function in a functional way, right? It's called functional programming. Uh, and that class also will talk about parallel programming as well. And so embedded system where in this if you take IoT class, I think Ajahn Piti is teaching this class, right? Many of the content in the IoT class would be governing embedded system. This is kind of like a basic building block for IoT. I talk about IoT as a system building topic, right? So that's where many of the problem would emerge. And that's where the hard things that are unique from typical embedded system. Embedded system is like you have a low power device like Raspberry Pi or NVIDIA Jetson or even Arduino or a microcontroller, right? The topic would cover how to read the input data, process the data, and control the device, right? It also can involve kernel hacking if needed, because sometimes you need to rewrite some part of the OS to make sure they are really efficient. Assembly can be common in some cases because you also have to optimize your code by hand. And the task scheduler gets really more important because you have this thing called real-time deadline. What are the example of real-time deadline? Self-driving car. Anyone heard about this, right? Autonomous driving or self-driving car. Which tasks are more important? The tasks that control my air conditioning in the car, the tasks that figure out the path for the car, or the tasks that are trying to detect the object in front of me. Which tasks are the most important? Oh, what's kernel? Okay, my bad. Kernel is kind of like a core, like the word kernel means core, right? It's a core software that run the computer, right? For example, in Linux, that's a part of the code that's called Linux kernel. That's where many of the control of the hardware, the code that controls the hardware would reside. So hopefully that's like a general enough explanation. I'm sorry about not having to go deeper in this because we don't have time for that. Great question for sure, but this is like a software that kind of control your computer. It control the operation of the computer. And then there'll be another piece of software that you write in Python and Java that would run on this piece of software again, right? But yeah, let's go back to the question. Now you have self-driving car with multiple tasks that you have to run, right? Detecting the object in front of you is probably more important than figuring out if you need to turn left or turn right. Because I mean, you can go straight for sure, right? Um, that is probably way more important than controlling the AC, the air conditioner, right, of the car. So you have to now figure out where is my deadline. When is the last seconds that I can have to detect what's the object in front of me, right? So that's embedded system. Starter system is more like how to manage the file. Why is this important? Why is this an area, right? Because this is where and why the program gets slow. Every time you have to go to the disk, it's slow. So it's good to be able to manage your data in a way that is fast, right? Some of the key issues are throughput. Throughput is how many bytes you can read or write in 1 second. Reliability. What happens if my disk crash, right? If you run a server, you can, I don't think you can tell the user, hey, sorry, my disk crashed. Your program that has been running for 24 days crash with them, right? You cannot. So how do you build a system that are reliant? Not reliable, right? Latency, how fast can you access a file, right? What are different topics? Parallel programming. These are more on the you have multi-core, you have the GPU. How to take advantage of that? How do you generate the parallel tasks? How to change the algorithm to make sure they can be run in parallel? How to be aware of the hardware constraint and how to deal with say data synchronization. Many people want to modify the data. What do I do? How to reduce the sequential bottleneck there's quite a number of language and framework that support parallel programming. You will learn the language called Rust in the functional and parallel programming. There's also Silk and OpenMP. These are for parallelizing loops. There's CUDA and OpenCL for the GPU. If you are interested in parallel programming, especially if those of you who want to do parallel algorithm, definitely talk to Ajahn Kanat. He's the world expert in this topic. He's one of the forefront of the research in parallel algorithm. So definitely check with him. If you want to talk more, okay, how do I design the hardware for these type of parallel program? then you should talk to me. Because that's where my expertise reside, right? So that's actually um that's actually get close to my topic, right? I can safely for sure tell everyone here that in this country I'm the, if not the most expert uh, on this topic, right? I do have many publications to top venues. I know about this topic. I learn about this topic at CMU. I work on a group that has so many works on computer architecture. So I want to kind of also talk about what is computer architecture, because we do free time. Today is the last day of class for this semester anyway, so I kind of want to motivate what did I do, right? The reason behind that is partially I want to kind of talk about why do I talk about this and why do I mention computer systems, right? So let me go back to why, right? Why you should care about computer system, which are these topics, right? So if you talk to professor in Thailand, especially those who work with the industry in Thailand quite a lot, you might have heard about the discouragement to say, hey, why are you working on computer system? There's no job here. Well, it's an area that even in Thailand is not a lot of expert, right? They don't know what computer system can do to give value to the company. But I would assure you of this, right? Most, if not all, major company in the world that are tech company. I'm sure you all heard about Apple, Facebook, Google, Microsoft, Amazon. What else? Like Intel, AMD, Nvidia, VMware, any major tech company that you are aware of has a really large team that work on computer systems. In China, that's Huawei, Alibaba, right? All those companies would also have Xiaomi, even, right? They would have people who work on distributed system, computer system, even at like TikTok, for example, would have people who work on computer systems. If you want to scale your IT infrastructure so that you can compete with this giant, you need to have a team who knows this topic, right? So you might have heard about some discouragement about going into this area. Uh, yeah, sure. That I'll definitely follow up with that. Uh, so so I'll follow up with that when I talk about architecture, actually, because that's actually the topic of architecture, right? And let me first wrap up about the computer system. So if you want to work on computer system, you find fun in like hacking kernel, working with the database system, working with computer network. Don't feel that you're not going to have a job. You will if you do it well. You are likely to get a job at the major tech company because there's a demand for sure. There's quite a big demand. You just need to make sure you make yourself visible so that they can detect you that hey, that's where you are and you can contribute to the company, right? Uh, it is a large area, right? And I see the future of the IT industry and computer industry in Thailand. They have to also have more people who work on this area, and I'm kind of worried, right? Right now, there's so many snake oil salesmen, including professor from university who doesn't really know what they're talking about, right? I mean, look at blockchain, right? There are certain elements that's great about blockchain, but there's also a certain trade-off that come with it, right? There's so much of the performance trade-off that have you even considered a system point of view when you look at blockchain, like how to scale, how to make them fast, right? If you want to go out and buy like grilled pork, like muping or something at the market, right? You probably don't want to wait forever to verify your transaction, right? And if you use platform like BitCup, for example, to trade, right, to exchange the currency, now you basically get rid of all the decentralized advantage because it becomes centralized again. Defeat the whole purpose of having cryptocurrency. So what's the solution? I don't know, right? it's still something that we have to look into. Like, okay, how do we have a better solution? Because right now, I think my opinion is the current solution is not that scalable because we need a better solution. Uh, but anyway, so now let's go back to your question. The question is about like how does Apple and other companies like Intel and AMD design the chip, right? How can you make them efficient, right? Um, it's a great question because this question kind of lead into this topic of computer architecture, right? I mean, it's not magic. The way you design chip is not magic. That's, I mean, these are, I would call this area one of the oldest topic in computer science. It just happened that not many people, if to be honest, none, except for me, are actively working on this area, right, in this country. So that's why if you're here, you might not have heard too much about this topic. Uh, but uh, the area basically would govern the theory behind how to build chips, right? So let me kind of first motivate by this picture. Have you seen this before? Do you know where this is? Like what is this building? The Louvre. Thank you. Yes. Oh, that's really fast. Section one takes some time. There's a student that has been there and he forgot the name. Um, so this is the Louvre, right? You can see that this is like major piece of architecture, right? It's a really great architectural work that built this really beautiful building. Fun fact about this: I was in Paris for a conference, for architectural conference. I present my work and I get some spare time in the evenings. I walk around and I went to the Louvre. I mean, sadly, it's closed by that time, so I didn't get to go in there, but because I did take a lot of pictures, right? So I set up my camera and take this picture, and it's like, hey, this is really beautiful, right? I mean, the building is beautiful, and I'm not talking about my picture. It's like just a really, really normal picture. But this is a major architectural piece. They serve multiple purposes. These serve as the way to house many, many important pieces of art in the world, right? So you would design it so that it really reflects what they are designed for. It's look beautiful. It's secure because most of the stuff are inside this pyramid, right? It's actually downstairs. So you go down, so you kind of protect everything from the elements, right? Uh, so this is a piece of architecture. You built something for certain purposes, right? What's this? Another historical picture, as in like there's a story behind this that involved me at Kanat, right, and many other of our friends. So we went on a hike near Pittsburgh. The area is called Ohio Pile, right? And Ajahn Kanat told me that there's this waterfall called the Kim Copper Fall. It's easy to go down to, but it's really, really picturesque, right? It's not big, so that you can kind of fit everything into this picture, right? So we set up a tripod. He also take a lot of pictures, like I do, right? Back in the day. I'm not sure whether he did that these days. Um, but yeah, we set up a picture, we take this. And the reason why I show this is like around that area, there's also another place that has waterfall like this. But then there's like a rich guy that come in and say, hey, I want to build a house on a waterfall, right? He then talk to a really prominent architect, and the architect built this building called the Falling Water. It's actually now a UNESCO World Heritage Site. It's a museum. You can go there and buy a ticket to walk and to get a tour of the building. It's awesome in there. Every single room has a purpose. Every single area has a purpose, and the architect design is such that they know what the user want. They want to encourage the people in the house to walk out and enjoy the nature. So they design this building in a certain way that encourage you to go to the balcony and look at the awesome surrounding greens and the water and everything, right? This is a masterpiece again by a guy named Frank Roy Wright, right? So this person is a really prominent architect in a similar way as how we treat like Dijkstra, right? For example, it's like a prominent computer scientist. So Frank Lloyd Wright built this house, and why do I talk about this, right? So architecture, computer architecture, similar to how people build houses, right? We design computer, we design computer, and hopefully what's coming up next would answer your question, right? How do I design computer? So first, I would kind of understand how the circuit works, right? Electron will flow from uh, one place to another in certain way, and this is how the transistor work, and this is how I can store the charge, the electrons. If I put the transistor in this way, then if you know the high level concept, you can put together a circuitry, right? And then you have to understand the software. From Apple point of view, what are their core customer? So let's say you build an iPhone, right? How do you figure out what should I put on the iPhone chip? I would then look at the typical software running on a phone, right? I would look at typical software running on a phone. I would work with people who are working on the OS, the iOS. Then I would check the I'll check with the people who work on circuits and material science. Like, okay, what are the current awesome material I can use for different purpose for my chip? Then, then in the next class, the computer system and architecture, we will learn how does the program read assembly that you learn in this class, the assembly code that you learn. How does the computer figure what these components are? What are they add? How do I tell that's an add? If I know that's an add, how do I build the adder? We are not going to talk about how to build adders. That's a little bit too low level because most of you are not likely to be doing this, right? So, but I will talk about the high level concept of how can someone design a chip, computer chip, right? The work that we do would kind of go over, okay, we know there's emerging application that people would use like machine learning, IoT. These are the new type of software. And then I know the trade-off of the current hardware. I know the design of the current hardware. So these, some of them are trade secrets. How do I build this component in DRAM, or how do I build this component in the M1 chip? Some of them can be trade secret. Some of them are known. Some of them can be guessed, to be honest. Like I look at the spec, like, okay, that's how they do it. So there's a lot of theory that go behind how to build chips. There's a lot of theory behind how to build a typical CPU. There's a lot of theory behind what's the fundamental concepts behind the GPU. So these are what we do actually as a computer architect. So we just look at this, then talk to the user and build something that match your demand. So hopefully, I know that this is hand wavy. So hopefully this kind of answer your curiosity a little bit. But to answer that, some of the part we know, many of the theory behind it we know, many of the hypotheses you do, if you build the cache this way, it will be good in terms of dealing with this type of application. We know that to put them together into the chip, so we'll just pick the techniques that known to work well with certain programs that are as basically we would assume that would get one on say an iPhone or MacBook, and then we'll build the machine based on that assumption. So hopefully it clarifies some of this question. I'm not sure. Like, is it an okay explanation? All right. So yeah, and thank you so much for that question because I have to be honest here. Like, there's not a lot of architect, right? And I'll right. Okay. So now that we talk about some of the side discussion, now let's come back to our topic and do some final exam review, right? So before we go through the sample exam, let me first talk about the format. So I will release the exam at 11:59 p.m. on Monday. You have until 11:59 on Thursday, 3 full days to work on it. There'll be a live session next Tuesday between noon to 4 p.m. for the Q&A. Uh, any further exam related question is sent through email. Quick caveat. I'm expecting a child in 2.5, like around 3 weeks actually. Yeah, 3 weeks. Not not earlier, hopefully, around 3 weeks. So my schedule these days is really hectic. Like I need to make sure my house is ready for a child. It's not right now. It's a mess. Like I don't. Yeah, I don't want to show you my house. Actually, I was about to like turn the laptop so that you can see how messy it is. But now I'm ashamed to do that. So I need to like build a lot of IKEA furniture and so any further exam related question, please do email me. But I do encourage you to come in at noon to 4 because you will see the exam already. I will answer the questions because my response time depend on my work schedule and my life schedule. Next week and going forward, my schedule is probably hectic until January. Um, Great study materials from our in-class exercise and assignments 3 and 4. And here are the topics that we can have on the final. Data representation, program representation, assembly, program and data are on DRAM. So the fact is this is something that you should be aware of. The memory hierarchy, cache, virtual memory. The sample exam doesn't have assembly question. I did have that in some other semester so they can show up, right? They can show up. The concept like a jump table, it can show up. I guarantee you that's one free question that you should know. What is the TLB? So if you don't know what is the TLB, go to our virtual memory lecture. Specifically, the second part of the virtual memory lecture, we talk about the TLB. All right. And before we leave today, I will show you the sample example. No, there will, yes. Here, assembly on the final. So there can be assembly on the final. Sorry, guys, if that's not clear. There can be assembly on the final. I am not going to ask you to write assembly code on on the machine. It's not a programming card. So if I might be like fill in the blank kind of thing, if you know what I mean, or like explain what does this do, kind of question, if you get what I mean. But I'm not gonna ask you to like write a assembly file that run and do this, right? That's a little bit too hardcore. Okay, so now I'll have a 10 minutes break and we'll switch back to the final the sample exam from previous semester. So let's resume at 3:20. We will be back and we'll talk about the sample exam. I'll stop the recording right now